Hi, everybody. It's Professor Mitchell. We're almost to the end of Chapter 12. Today, we're looking at Section 12.7 on common logarithms, natural logarithms, and change of base. There are two logarithmic bases that occur so frequently in applications that they are given special names. Common logarithms are logarithms with base 10, and natural logarithms are logarithms to base e, which is an irrational number that is approximately equal to 2.71828182845. All right. Now you might be thinking, well, what's natural about that? And my answer is you'll find out at some point through calculus, I think at the beginning of Calc 2. All right, so let's start with common logarithms. When you see log x, with no base indicated, that means base 10. So this is just shorthand notation for log base 10 of x. You can use a calculator to approximate common logarithms using a button that is labeled log. And to find exact values of common logarithms, use the definition of logarithms to rewrite the expression in exponential form. All right, so let's start out with using a calculator. In this problem, they want us to use a calculator to approximate log 9 to 4 decimal places. This is absolutely a calculator problem. So depending on what kind of calculator you have, you're going to either press 9 and then press the log button, or more commonly, first press the log button and then press 9. So let me show you how it works on my calculator. Okay, on this calculator, we're going to press the log button first and then press 9, close the parenthesis. And to 4 decimal places, that value is approximately 0.9542. All right, which you can see here. All right, properties of logarithms, which we learned about in a previous section, the ones in the left-hand column. Log base b of 1 equals 0, log base b of b to the x equals x, and b to the power log base b of x equals x. Those can be written in terms of common and natural logarithms. Remember the special shorthand notation for common logarithms. Just imagine that there's a little subscript 10 here. And then natural logarithms, I haven't introduced you to that notation yet. Okay, so we'll come back to natural logarithms in a moment. In the meantime, we have this example. Find the exact value of each of the following logarithms, and we're going to try not to use a calculator for this, okay? So the first one is log of 10,000. Remember that this means, since it's base 10, to what power do you have to raise 10 to get 10,000? All right, so after you think about it for a minute, you realize that 10,000 is 10 to the power 4. So using one of the inverse properties that we were just looking at, I think it was property number 2, log of 10 to the 4th equals 4. All right, and then similarly, log of 0.001. 0.001 is 10 to the power negative 3. If you remember learning about scientific notation, that might help you with this. And using that same property, log of 10 to the power negative 3 is negative 3. And then finally, we have log of the square root of 10. Remember that the square root of 10 can be written as 10 to the 1/2. So using that same property number 2, log of 10 to the 1/2 is just 1/2. All right, next we have solve log 3x equals 1.3 for x. We'll give an exact solution and then we'll approximate the solution to 4 decimal places. All right, starting with log of 3x equals 1.3, we're going to write this equation in exponential form. And here is where it might help to imagine that little subscript 10 there. Remember, if you don't see a base, it means base 10. So writing that in exponential form, you get 10 to the power 1.3 equals 3x. And then if you divide both sides by 3, you get x equals 10 to the power 1.3 divided by 3. That's the exact solution. And when you put that into the calculator, you find the approximate solution is 6.6509. All right, that brings us to natural logarithms. Natural logarithms are the ones that tend to work the best in calculus. You're going to be using these in calculus more than any other kind of logarithm. So the notation ln means natural logarithm, which is log base e of x. And again, you can use a calculator to approximate natural logarithms using the ln button. I'll show you that in a minute. And just like with common logarithms, to find exact values of natural logarithms, use the definition of logarithms to rewrite the expression in exponential form. All right, so now we'll use a calculator to approximate natural log of 6 to 4 decimal places. This will work exactly the same way that the other problem worked, except use the button that says ln instead of the button that says log. All right, so let's try that on our calculator. Let's see, here is the ln button. I think on every single calculator I've ever looked at, it's one button away from log. All right, so to 4 decimal places, that's going to be 1.7918. All right. Okay, find the exact value of each natural logarithm, starting with natural log of e to the 4th. So this is, again, using that property number 2. ln of e to the 4th would just be 4. Natural log of the cube root of e. Remember that cube root of e can be written as e to the 1/3. Natural log of e to the 1/3 is just 1/3. So let's have another look at that slide, this one here. All right, so looking at that right column, these are all the natural logarithm versions of the properties that we learned about. I'm pretty sure that was in section 12.5. The natural log of 1 equals 0. Natural log of e to the x equals x. And e to the power natural log x equals x. All right. Here we go. Okay. So in this problem, we're going to solve natural log of 2x plus 5 equals 3.4. And again, we're going to give an exact solution and an approximate solution. Starting with natural log of 2x plus 5 equals 3.4. First, we'll write that using exponential form. Remember that natural log is log base e. And if you need to write that as a little note to yourself when you're first doing this, that makes perfect sense. So when you write that with exponential notation, it's going to say e to the power 3.4 equals 2x plus 5. And then they kind of did two things in one here. First, subtract 5 from both sides. You know what? Maybe it would be a good idea to write that in. All right, I'm not going to try to make it look super fancy. E to the power 3.4 minus 5 equals 2x. And then divide both sides by 2. And that will give you your exact solution. which is e to the power 3.4 minus 5 all over 2. Sorry, I'm trying to find my mouse here. There we go. All right, now for this one, I think it would be worth switching over to the calculator to show you how they get this approximate solution. So let's go back to the calculator. Let me clear out some of this stuff. Okay, so we're trying to evaluate e to the power 3.4, subtract 5, and then all over 2. So if I want to put that all in one step, I'm going to start with a parenthesis. And then I'm going to press second ln to get e to the x. My calculator automatically prompts you for the exponent. 99% of the time when you use the E button, you're doing e to the power something. That's almost the only thing we ever do with the number e is raise it to powers. Subtract 5, close off the parentheses, and then divide by 2. All right, and there is that approximate solution to 4 decimal places. It's 12.4821. Excuse me. All right. So now let's talk about compound interest. This is a big application of exponential functions. I think we've talked about this before, actually. So remember that after t years, the balance A in an account with principal P and annual interest rate R, written as a decimal, is given by the following formulas. You only see one formula here so far, but we're about to pick up another one. If there are n compounding periods per year, that formula is A equals P times 1 plus R over N to the power nt. All right, so here's an example, which I'm going to work out on the tablet. A sum of $10,000 is invested at an annual rate of 8%. Find the balance in the account after 5 years, subject to quarterly compounding. All right, so switching over to the tablet. Got this problem all ready to go. Okay, so we're investing $10,000 at 8% interest for 5 years with quarterly compounding. So the formula is A equals P times 1 plus R over N to the power NT. All right, so just labeling these numbers, what goes where. The amount being invested is P. 8% is R, but don't forget we have to change it to a decimal. Don't put in a number 8 or you're going to get a really crazy answer. 5 years is T. So that just leaves N. Remember, N is the number of times per year that the interest is compounded. Since it says quarterly, that means N equals 4 times per year. Okay, so we have 10,000 times 1 plus 8% as a decimal is 0.08 divided by 4. And then we're going to raise that to the power 4 times 5. All right. You know what? Let's just switch over to the calculator. I'll show you how you can put that all in the calculator all at once. Let's clear this out. Okay, so we have 10,000 times 1 plus 0.08 divided by 4. Okay, and then we have to raise that to the power 4 times 5. Now, if you're using a different kind of calculator, you may need to put that 4 times 5 in parentheses. Okay. So play around with the calculator and just see what works. And you will know that you are doing it correctly when you get this answer. And since this is an amount of money, we will round this off to $14,859.47. All right, so $10,000 invested for 5 years. We end up picking up a little bit more than $4,800 extra dollars from our interest. So I'll just show you that here. All right, and now I think we can switch back to the presentation. All right, so very interesting question. Suppose that I just opened up a bank down the street and I'm trying to get everybody to quit their bank and open an account with my bank. And suppose that my marketing gimmick is I'm not going to compound your interest quarterly or monthly or even weekly. I'm going to compound your interest 100 billion times every second. So do you think I will have people flocking into my bank thinking that they're all going to become billionaires? Well, maybe. Will they actually become billionaires? I don't know. That's what we're about to find out. So let's suppose that we invest $1 at 100% interest for 1 year, just to make the formula nice and simple. So the compound interest formula that we were just looking at becomes A equals 1 plus 1 over n to the power n. Now I have to toot my own horn here a little bit. I'm kind of proud of myself. When I'm showing this slide in a face-to-face class, or at least it used to be this way, maybe it won't have to be this way anymore, I would put a table up and I'd say, okay, don't look at the whole table, just try to read it line by line, because I didn't want to give away the surprise ending. Well, I figured out a way in PowerPoint where I can just show you a little bit of this table at a time. Okay, so what I'm going to do is I'm going to play around with different values of n, and I would like to encourage you to do this as I'm doing it. So for example, if I only compound your interest 1 time at the end of the year, then I think it makes a lot of sense that at the end of the year, your account is going to have $2 in it, right? On December 31st, I'm going to calculate your 100% interest, and that's going to be $1. So I'm going to add $1 to your account. Now, if I do it quarterly, this is where it starts to get a little more complicated, because at the end of, it would be April, I'm going to give you 25% interest. All right, so that would give you $1.25. And then at the end of June, I'm going to calculate 25% interest of your $1.25. So you will end up with more than $1.50. All right, this is where compound interest starts to make you a little bit more money. And it turns out, and again, I encourage you to check this, just put 4 in for n in this formula, you would end up with about $2.44. If we do it monthly, you'll end up with $2.61. If I do it weekly, you'll end up with $2.69. Are you going to become a billionaire? If I do it daily, you'll end up with technically a little bit more than $2.71. And if I do it every minute, and if you're familiar with a certain Broadway show, a certain song might be popping into your head right now, still just a little bit more than $2.71. And I'm wondering, does this number right here remind you of anything that we've talked about recently? 2.7182818285. Yes, I know it's not exactly that. If I compounded your interest once per second, it would be a little closer to that. This is our new friend, the number E, all right? Or very close to it. All right, so I really like this example because it shows you a kind of surprising place where E pops up, where you don't really expect it. Okay, and now that you've seen that, I don't think you're going to be too surprised when I tell you, okay, we've gone over this compound interest formula. But now if I open my new bank down the street and I try to lure customers in by telling them, forget even 100 billion times a second, I am just going to continuously compound your interest. Imagine a clock, you know, where the hand is just going around all the time. Okay, at the end of the year, it's going to add up to 8% interest or whatever, but that clock is always running. Well, it turns out that the amount of money in that account can be calculated, too many C words here, using this formula, A equals P times E to the power RT. Okay, so what I would like to do now is return to the problem that we just did a little bit ago. A sum of $10,000 is invested at an annual rate of 8%. Find the balance in the account after 5 years, subject to continuous compounding. So is it going to be a lot more than what we got in the last problem? So let's go back to the tablet. And I've got this problem all ready to go. As soon as you see continuous compounding, that tells you to use the formula A equals P times E to the RT. Okay, so in this problem, P is still 10,000, R is still 0.08, and T is still 5. So now let's go to the calculator. And I've still got the previous answer up there. That might come in handy. Let's just get rid of this. 10,000 times E, remember second ln, 0.08 times 5. So instead of $14,859.47, I am going to end up with $14,918.25. Okay, so the answer to my bank question, if I open a bank down the street and try to lure people in by telling them I'm going to compound their interest 100 billion times a second, yes, I may lure in some people that never took Math C. But now you know not to be taken in by that. The much more important consideration is what is the interest rate, all right? So, you know, what I would probably do if I was, well, really trying to lure people in and also make a little bit more money is, or keep more of my money, is if the, you know, old mom and pop bank down the street is offering 8% interest compounded quarterly, maybe I will offer 8 point or maybe 7.9% interest, but I'll say, but that's okay, I'm compounding your interest continuously. And maybe people will flock into my bank thinking that that's going to be a much better deal. It might not actually even be as good a deal, all right? And I think you'll have some problems in your homework like that, where it's going to say, okay, which of these two things is going to make you more money? 8% interest compounded quarterly or 7.9% interest compounded continuously? I like problems like that. All right, let's go back to the tablet. Okay, so we have just one more thing to look at, and that is evaluating logarithms with other bases. The only two logarithm buttons on your calculator are log for common log and ln for natural log. So what if I hit you with a problem like this? Evaluate log base 5 of 47. So remember what this means. It's asking what power do I have to raise 5 to get 47? Well, gee, I don't know, because 47 is not a power of 5. 5 to the second power is 25. 5 to the third power is 125. So it's probably somewhere between 2 and 3. But let's talk about how to find a really good approximation for it, even though my calculator does not have a log base 5 button on it. So if I was doing this problem for the first time, and I want to make it clear, you're not going to have to do this every time. I'm just showing you where the formula that we're going to use comes from. If I call this mystery number x, x equals log base 5 of 47, and then I write that equation in exponential form, it would say 5 to the power x equals 47. Now I'm going to take common log of both sides, all right, because common log is something I have on my calculator. And that would tell me log of 5 to the x equals log of 47. And now x is the thing that I want to know about. So using my favorite property of logarithms, the power property, log of 5 to the x becomes x times log 5. So we have x times log 5 equals log 47. And if I divide both sides by log 5, I get x equals log 47 divided by log 5. That would be the exact value. And the approximate value would be about 2.3922. So before I show you the formula, I just want to point out, well, why did I use common log? I said it was because common log is on the calculator. I could have used natural log. If I really wanted to, I could have used log base 7. All right, I wouldn't want to use log base 7 because that's not on the calculator. So probably every single time you use this formula, you're going to use either common log or natural log. So this is called the change of base formula. And I really don't want you to pay any attention to this version. So let's just skip right over this. If you use common logarithms, log base b of m is equal to log m divided by log b. If you use natural logarithms, log base b of m is equal to natural log m divided by natural log b. So it's kind of interesting that those two formulas give you the same answer, and I promise you they do. Okay, so let's use this formula to approximate log base 5 of 1/6 to 4 decimal places. So using common logarithms, you get log base 5 of 1/6 is equal to log 1/6 divided by log 5. You know what, let's do this on our calculator, why not? You do have to be careful. Okay, log of 1/6. All right, and then I'm going to say divided by log 5. All right, and to 4 decimal places, that comes out to about negative 1.1133. Okay. And just to show you, it doesn't make any difference. I could have used natural logarithm, natural log of 1/6 divided by natural log of 5. Gives you the exact same answer. Okay? So when you're doing your online homework, if it matters for some reason, whether you use common log or natural log, they will tell you which one to use. Otherwise, it doesn't matter. Okay. And that's going to do it for section 12.7. We'll see you next time.